Good morning, everyone. So glad to be here. Hope you guys have been enjoying this summit as much as I am. So glad to be here at the track 3 in our software training of the IEEE PES YP Summit for the United States and Canada. Uh, I hope you guys got a chance to also take a glimpse at the keynote speech with David Kohler. It's been a really good session. But right now, I would like to introduce you guys to Kasun and understand a little bit more about EMT studies. So Kasun received his bachelor's degree from the University of Moratu at Sri Lanka, his master's from the University of Manitoba in Canada. Right now he's with Electranix Corporation, where he's mainly focusing on system studies, including large-scale EMT studies, weak systems, hybrid simulations, SSR, SSTI, SSCI, harmonics, TOV, TRV, lighting, and etc. Prior to that, he worked at the Manitoba HVDC Research Center as a power system studies engineer, where he performed many system studies and PES CAD model development. He has more than a decade of experience in power systems and has worked in multiple disciplines such as system studies, model development, Python automation, testing, and commissioning of medium voltage switchgears. Zoom, the floor is yours. And I'd like to start with the name of our session, which is Why Do We Need EMT Studies? Thank you.
Thank you very much. Good morning, good evening, good afternoon. Thank you, Augustus, for the nice introduction. Okay, so before further ado, let's get started with the slides. So I put a question mark in my title. Why do we need electromagnetic EMT studies? So hopefully, I will answer the question from my presentation. If not, we can discuss after that. Okay, my name is Kasun Samarawickrama. I'm from Electranix Corporation, based in Winnipeg, Manitoba. I'll give a little bit of what we do and who we are. Uh, we are mainly power system study consultant based in Winnipeg, Manitoba. We do a lot of system studies, power system consultant studies for many utilities, OEMs, developers, etc. So we have a very smart set of engineers working in mainly system studies based on EMT and RMS based studies as well. So uh, we have developed our own tools to work with EMT platforms and RMS platforms as well. One of them is ETRAN based tools, and we have our own internal in-house tools as well that we use for many scripting and automation and stuff like that. Okay, so let's get started. This is my outline of the presentation. First, I'll give a little bit of an idea of what is time domain simulation tools and what are the differences between RMS based and EMT based tools, and then solution method, that the tools that we use in day-to-day life. Basically, what are the solution methods that use in RMS base and the solution methods in EMT tools. And then a couple of examples of EMT simulation studies. And then a little bit of description, history, solution engine, and models and techniques of PSCAT EMT DC. And then uh, uh, some features that we use in ETRAN. That ETRAN is a tool that developed by Electranix itself to bring data into PSCAD originally, and then it developed to many levels like parallel simulations, co-simulations, and etc. So last two topics, parallelization and co-simulation, I'm going to slightly touch on these topics. Further details, actually we have separate presentations on parallelization and co-simulations, and many other panel discussion in the upcoming PS general meeting in Denver, Colorado. Okay, so This is a basic algorithm or the basic representation of a resistor and a inductor in a power system simulation tools. So in a RMS based tools or a transient stability tool, a voltage across this section, which is an R and a L, the voltage across this section we can write as equals V equals I into R plus j omega L. This is simply uh, Ohm's law V equals IZ. So when we have this representation, what we assume is we assume that impedance given in a certain frequency is fixed. So that is the main disadvantage when it comes to transients, when it comes to the changing frequencies. Because when we assume the frequency is fixed, we assume a sinusoidal waveform is a fixed frequency waveform. So that's the part that we missed if we do all of the studies or the studies that we need to analyze, especially the high frequency or a very small time step transients that we need to analyze to get an idea how the models ride through, how the models performs. So that's where the EMT comes in handy, because we model this the behavior of this inductor the to the closest to the reality, which is V equals I R plus LDI by dt. For a resistor, it's no different between the RMS tool and the EMT tool. It's a simply I into R. But inductor or a capacitor, which is energy storage devices, the the closest representation to a actual inductor or actual capacitor is a differential equation. This is LDI by dt. So once we model this one, we see things that we don't see in here. We see things that we don't see in RMS tools. So that's the most important part of the EMT tools, that we are looking at certain aspects of the system that we have this differential equations model to see that. So that's why EMT tools are needed. That's why we need EMT studies in certain aspects. So let's go to the. I have put few slides on why we need this and how this differential representation is required in certain studies. So in general, conventional traditional transient stability tools may overestimate or stability or represent protection control features in insufficient details. As an example, let's say in the RMS based tools, we don't have actual instantaneous waveforms method. These are all RMS based. So in a physical device, in an actual device where a protection is modeled based on actual instantaneous waveform, and then the sampling, and then the Fourier transformation, and all those things will calculate the RMS base, and then we'll go to the RMS based protection algorithms that they have implemented. So the first part is not included in the RMS based tools, because you directly have the RMS based solution or RMS based answer right at the solution engine. But that we lose some information that we required in filtering or a sampling that is not model, or in other words instantaneous base protection. So there are many devices that we have right now instantaneous base protection is available, so we cannot model those ones in RMS based tools. So that's one of the main disadvantages, because if you see in an RMS based tool, a tripping of a device may not be actually tripped in real system, or not tripping could be a tripping in a real system. So both could happen. But if we model these things in detail, that we can we can get a closer solution to the actual system. That's why we did EMT based modeling and EMT studies in power system analysis. In general, power system RMS tools or transient stability tools are in either 50 or 60 hertz frequencies. Networks are modeled at constant admittances. The not network admittance or the network impedance does not change with the frequency. Usually it is fixed, and then admittance matrix is calculated using all at fundamental frequency. So no subsynchronous or harmonic phenomena can be analyzed using RMS based tools. And it's pretty much based on positive sequence quantities. So the DC components are usually neglected, and negative sequence are not represented typically, but some tools have some tricks that can to represent the negative sequence in certain sections or certain areas of the network. So that's not exactly 100% correct, but because it involves some approximations. RMS based tools mainly protection is fully represented, and the PLL detail. This is one of the main detail that we miss in currently, because uh, with the renewable integrations, many grid following components, grid following inverter based resources are equipped with phase lock loops, which is instantaneous waveforms are essential to model these PLL details. So once we don't model this, once we cannot model this in RMS based tools, we basically lose a lot of information, or the right true capability. uh, as right true capabilities are not pretty much modeled with the RMS based tool. So that's why we need EMT based tools to model these details, um, to see how the models performs, how the inverter based resources ride through in weak systems, and so on. And one of the main limitation in transient stability tools, so the RMS based tools, are the large simulation time steps. So the PLLs, or the inner loops of control systems, especially new renewable based power electronic based controllers, are very fast, has very fast time constants, and which we need to simulate in small time steps. So that is something that we don't use in transient based tools, or the RMS based tools. We use large time steps, so we lose this information, or we cannot to represent details or the accurate modeling in RMS based tools. So we usually simplify the, the control loops to operate with larger simulation time steps. And the convergence issues. In RMS-based tools, you usually use numerical methods, or a Newton-Raphson, or a Gauss-Seidel, or many numerical methods, because it's iterative based. So every time step you solve a power flow solution, and it has convergence issues because of this iterative based approach. But in EMT tools, it's a simple solution. It's a simply solution, couple of parallel equations, but there's no iterative based methods are involved. So it is no convergence issues are observed, or there's no iterative methods or numerical methods used in EMT based solutions. And the and the limited converter electrical representation, that's also one of the biggest problem in RMS based tools, because most of the controllers we need to model simplified in RMS based tools, due to tools limitations, or the inherent properties of the RMS based tools. So all of these limitations uh, basically not exist, or is successfully handled in EMT based tools. So detailed modeling in general is required to see, especially nowadays with many weak system problems and things like that. We need to see in very high frequency phenomena, or in general frequency dependent phenomena need to be analyzed using EMT based tools. Okay, So let's go to a little bit of math, how we model these passive devices in EMT based environment. So when we have an inductor, so the voltage across inductor we can write as a differential equation compared to RMS base tool. We can write the V equals LDI by dt. In RMS solution plane, it is V equals I into j omega L. So how we gonna solve this equation? In RMS space, it's pretty much it's just dividing by the j omega L. You can calculate the what is the current. So if you have the voltage and the inductors given, you can calculate the steady state current. Once we have in differential equation, now we need to solve this equation to calculate what is the current through this inductor, because current through the inductor is a differential equation. So once we arrange this equation like this, so what we're going to do is we're going to solve for the current, and then this integration we can write the equation like this, and then we integrate the instantaneous voltage using trapezoidal integration. Trapezoidal integration is something, it's piecewise linear integration method. If you can see in this picture, let's say we have a waveform like this, and then we need to integrate between these 2 points, x1 and x2. So what we do is, in in theory, the integration is basically the area under this curve. So area under this trapezoidal is basically this height plus this height multiplied by this h, and then divide by 2. So that's what we have modeled here. So Vt plus Vt delta minus t divided by 2 into delta t is the area under the curve, or the trapezoidal integration of this integration. So once we do that, we can rearrange these terms such a way that we have uh, present time step voltage and previous time step voltage and previous time step current. So when we rearrange these terms again, what we can see is the present time step current is equal to some constant multiplied by present time step voltage plus some history terms. So what I'm saying as history term is, these two terms are based on the previous time step information. In other words, this is the previous time step voltage. Vt minus delta t means previous time step voltage, and it minus delta t means previous time step current. So there's a constant multiplied by the previous time step voltage plus previous time step current. So this entire term is based on previous time step information. So we can say this as the history current representation, and this is voltage. So so this term in units wise, this term has to be a current. So this is the admittance of this network. So we can represent this equation with a resistor and a history current term. In other words, the current through the current through inductor here is the current here. So we have some voltage across it and some admittance. So we can represent this part as a resistor, and then there's another addition of a history current across it. So when we add this history current plus the current through the resistor, will give the total current through the inductor. So what happens is, when we convert an inductor to a resistor and a history current, now this representation, we no longer have differential equations. What we have is a simply current addition. So we change this differential equation to a difference equation, or simply we can add these currents and solve this equation. So this is the main idea. This idea is originally invented by Dr. Herman Dommel. He's a professor in UBC. So this is the basic idea of representation differential elements in EMT based algorithms. So The similar representation is done for the capacitor as well. So for the capacitors, we can write the current equal to C dV by dt, similar to voltage of the similar to current of the inductor. Now we have the differential equation of the voltage. So similar trapezoidal integration is applied, and then once we rearrange the terms similar to the previous example, and then we can represent a capacitor also with a resistor and a history current. So now this resistor term is 2 delta t by 2c, and the previous inductor current is 2L by delta t. So both capacitor and an inductor we can represent with a resistor and a history current in the EMT based platform. So in other words, what happens is this circuit represents here we have an inductor, we have a capacitor and resistor and sources. This entire circuit turns into a circuit such a way that it has only resistors and current sources. So to solve this circuit is very simple. So it's simply applying Kirchhoff's law. So you have some current sources and resistors. You don't have any integrators, or you don't have any differential equations here. So simply you can solve this equation and get the currents through the each branch, or the voltage in each nodes, and so on. That's why I mentioned previously, we don't in EMT platforms, we don't have any iterative based solutions, so we don't need any numerical solutions to solve these equations. These are simply three parallel equations we can solve and get the answers. So, and at the same time, we have also modeled the the the, the the differential nature of the inductor and the capacitor as well. So there are more information modeled in this circuit, and it is easy to solve. So that's the main advantage of EMT based platform. This is a simple representation simulation that I've performed for a simple inductor. So in a normal RMS based tool, when we close this breaker, the current through this branch is simply V divided by R plus J omega L. So which is in the first time step, at the time that you close, the current goes to the steady state value. But in reality, this is an inductor. So this has a resistance to the rate of change of current. So in reality, what happens is when you close this breaker, the current gradually increase and comes to the steady state level. So that's why we see that's a ramp, and this time constant is L divided by R. So in RMS representation, we see this as the green curve, and in the EMT representation, we this as a smooth curve with a time constant of L over R. So similarly, the same thing if you do with the if you energize with the sinusoidal waveform that you can see in the RMS based tool, you have a step response kind of behavior, and the EMT based tool you have a slightly overshoot, and then it's settled to the value that we have in the RMS based tool. So this initial transient, or this initial behavior of the current, or the initial behavior of the voltage, is the key thing in transients. So when we lose this behavior, we lose many things, or we don't see many things that we should have seen. So that's the main idea why we need EMT studies. This is the same thing with the capacitor. So now we can see the capacitor charging time constant. So because since this is a capacitor, right after this closing this breaker, this will not go to the voltage of this source. It'll gradually go. Once this voltage will become this voltage when the current stop flowing, or the capacitor is fully charged. That's why you see this gradual uh, increase of the voltage. So similarly, this is for the AC source energization of the capacitor. Here are some examples or some example studies that EMT is required. Electromagnetic transients are required to model the lightning and switching over voltage studies. These are like, if you assume a situation like a lightning strike on a transmission line, and then we need to see how the voltage increase, and do we have enough BIL is enough to stop the restriking, and so and so we need to model all these details in EMT domain to see these the fine details. That's this one of the high frequency study, especially done in EMT. This is switching is slightly lower than lightning frequencies, but still high frequency phenomena. And then there are many studies. The EMT modeling is required to see these essential behaviors: temporary voltage, breaker, transient recovery voltage, and secondary current studies. And this part is basically with the renewable integration. There are many more things that we did not see in traditional power system studies, but we right now we see, and we see many problems as well. So to see these issues, we need modeling in EMT. So especially inverter based resources dynamic performance, the interactions with the nearby plants, interaction with the synchronous machines, and then fall right through whether the inverters or the devices will ride through a temporary faults, and the dynamic performance of the fax devices, um, and especially HVDC transmission applications, and others few other studies like black star studies, system harmonic and power quality protection, and subsynchronous studies, and so on. So this is only a example list of studies. There are many more studies involved in EMT scope. This is one of the plot of a transformer energization study. So uh, in transformer energization, we when we energize a transformer, we know that we have a inrush currents, and this inrush currents, the magnitudes or the voltage dip at the connected bus. These are essential to see if we have especially parallel transformers. Then we need to see the sympathetic inrushes, and so and so we need to basically model very fine details, including transformer saturation, and how we have the resonance fluxes, and uh, uh, detailed representations of the transformer and the system is required to see these things. So that's why we need EMT type of simulations to analyze these kind of phenomena. EMT programs. So we have this is a list of EMT programs that have in uh, one of the main EMT programs available right now. I think there are many other programs as well. These are the some main programs: PSCAD, EMT DC, EMT PRV, and Power Factory Silent, and RTDS and Opal RTR. True real-time digital simulation as well is also use EMT-based platform. And since I have used mainly PSCAD as a EMT tool, and other tools also. I'm not gonna compare tools here. Uh, just gonna my own experience. So the rest of the presentation will be based on PSCAD EMT DC software. This is a little bit of a history of PSCAD EMTDC. It's originally developed as only EMTDC. There was no PSCAD part at the beginning. It was electromagnetic transients for DC. Originally started by Dennis Woodford. He's our president at Electranix right now. And in 1975, so this is this goes back to much more than simply renewable integration software, because this is originally started for HVDC originally developed for Nelson River HVDC system analysis, and then it gradually developed with many other addition, and then nowadays we use for many applications in throughout the power system analysis. So development or the development of PSCAD, the PSCAD. So actually PSCAD comes when we have the GUI at this stage. EMTDC, there was no GUI, only the solution engine was there, and then those were used in mainframe computers and then punch card and so on. So with the introduction of PSCAD, which is the GUI part, and then we have the solution engine and the GUI. So now we can see things in PSCAD itself. We can see the plots, we can see the real-time numbers, how it when the simulation is in progress. And originally developed in Linux, in a Unix base. Many utilities, consultants, universities used this application, and then version 3.1 released for the PC, Windows base, and version 4.1 is one of the most stable PSCAD version, released in 2006, and many released after that, and currently we use version 4.63 and version 5.01. So these are the latest PSCAD versions up to date. This is the EMT. Give me a second. This is the EMTDC solution engine. This is how the EMTDC algorithm works. All the power system devices or the solution for the electrical controllers are solved in this subroutine, distance subroutine, and then calculates the information required to solve the I equals YV equation. So to solve this I equals YV, uh, as I explained in previously, we need to calculate the history current. So all the components in the network devices in the EMT domain is modeled using resistors and history current or current sources. So this part is the part that we calculate all the history current parts and solve any custom models or any PSCAD models here. And once we have these arrays, so we solve the network. The solving network is basically calculating the voltage at the current time step. So basically in this equation, I is the history current and Y is the admittance matrix. This admittance matrix is simply resistors. So because in the network, once we model all the differential devices and the resistors, all reduces to resistors at the end. So what we have is simply a real matrix here, and then we have the unknown voltages, so the voltage that we are going to solve for. So once we invert this matrix, we can calculate the unknown voltages, so the voltages, and then at the DS out, we calculate the outputs, basically what are the RMS voltages, so powers, currents, and so on. So that this is, and then it goes to the next time step, again calculate the history currents, and this keep going on. So this is how EMTDC algorithm works, and that's how we see every time, like this is the part that we get to see the plots, get to see the instantaneous voltages and so on. And EMTDC PSCAD EMTDC master library, there are pretty much covered all the components that we need to model a power system. T lines, cables, transformers, control box protection sequences, logics machines, HVDC, and many more other things, data handling, plotting, recordings, and so on. So if you need to model a PSCAD, if you need to model network in PSCAD, you can put together a model from using these components, and you can pretty much model anything you want in a power system using these models, except for custom models. Custom models are a different topic. Those are I'm gonna roughly touch in a couple of next slide how the custom models come into the PSCAD. Transmission lines, this is one of the main component and one of the complex component in PSCAD. I would say there are three transmission lines. available: bisection, Bergeron line model, and the frequency dependent model. Bergeron line model is a bisection model, but we can assume something like this. A bisection model is simply R, X, and B. So you have a series connected resistor and a inductor, and then shunt capacitors. Bergeron model is, we can say, infinite number of bisection, or when we put together we can get the Bergeron model, similar representation like Bergeron model. So it's a distributed parameter model, but we can assume many bisection put together is what we have in the Bergeron model. The most advantage of this, the biggest advantage of the Bergeron model is we can build using simply RXB data or the power flow data, because usually in when we do EMT studies, the data that we get to do EMT studies is coming from a RMS based tool. So the data that we usually have is RXB. So then we can use this RXB, but still represent a frequency response of a transmission line using the Bergeron model. And then the next one is the frequency dependent model. This is the most detailed modeled, I would model in the PSCAD. It can model basically right of way data, transmission line conductor characteristic like the DC resistances, sag, the dimensions between conductors, transmission tower resistances, many more details. When you put all together, it calculates the RXB, or system resistances and inductance and capacitors for each and every frequency uh, through frequency dependent model. So this is one of the most advanced model. If you do especially like lightning studies, or studies that high frequency part is important, this is the model to use. So that's one of the main model in PSCAD EMTDC. This is how it looks like inside when you go to the transmission line model, detail frequency dependent model. You can give all this information, the transmission line lengths, heights, distance between phase conductors, uh, electrical data of conductors, and then you can solve this all this information goes to line constant program and then calculates RXB at each frequency, and that will be used in that will be that we use to curve fit to get the EMT model of the transmission line. This is one of the technique used in PSCAD. One of the most important technique, I would say, used in PSCAD, interpolation. Especially when we have these renewable devices, there are many devices involved with switching. So switching is one of the important thing that we need to represent. As an example, if we represent as a full converter with IGBTs, so we need these IGBTs to switch in specific timing, that those timings are coming from the IGBT order. IGBT switching on off command coming from the controller can happen between two time steps. So what happens is, when we don't have interpolation, basically at this point, let's say the diode current is positive, so it's not the current is not stopped, and the next time step the current is negative, so it understood, okay, the current should not go to negative, then it goes to zero, and then it stays at zero. So this is the behavior if we don't have interpolation. But in reality, what happens is it goes to zero and then it stays at zero. So let's say this is an ideal diode example. What what interpolation does here is, in PSCAD, it calc it it goes to this time step. Okay, check whether it's anything need to be switched in between two time steps. So yes, so in this example, this has to be switched here. So it goes back to the point that it should have been switched, and then go one time step forward, and then come back one time step back, and then keep going forward as usual. So with that exercise, basically we go back and then come back to the exact switching point this waveform can be achieved. So this is very important, because when we don't have this exact switching, many instabilities and many problems uh, uh, can be observed. And since we have this interpolation technique, the time step dependability is is not there. So basically, an actual inverter or actual device, actual model or actual wind farm runs in their control system runs in a certain time step, and the PSCAD simulation we can run in a different time step, but still use interpolation technique and get a correct solution for this one. So that's why I said this is one of the most important feature in PSCAD. It's been there for more than uh, 20-30 years. So this is the technique developed after Windows Windows EMTDC. ETRAN. So this is another tool which is important when we do EMT studies. This is developed by Electranix itself. EMT studies is basically we do certain types of studies. How we get this data to perform these studies? So the data comes usually in RMS based comes from RMS based tools, because utilities in general have many types of RMS based tools. So those data is exist. So if we are to model something in power system looking at RMS based tool data, then we simply manually put everything together and create a system in PSCAD. That is very time consuming, and sometimes it's impossible to do, like if you are involved with hundreds of thousands of buses. So this is where the ETRAN comes in handy. So you have your power flow data, then ETRAN bring those data back into the PSCAD using data conversion, basically create the PSCAD case from power system based power flow based tools, and then we can start with a uh, good case which is initialized properly, and then we can run the simulation in PSCAD. So this is the first this is how the ETRAN is started to bring the PSCAD to bring the PSSC or RMS based tools data into PSCAD, and then there are many more things developed after this: parallel simulation, co-simulations, uh, and many other models were developed in ETRAN. Basically, uh, in terms of PSSC, like PSSC, all the dynamic models are model in ETRAN libraries, and then you can bring any PSSC generic dynamic model into PSCAD with a single click. So all the models are already modeled in ETRAN library, so it's very easy to bring, and then we can do the study in PSCAD. So that's one of the tool that is essential if you're doing large PSCAD studies in using power flow data. This is I covered. And basic ETRAN process is you bring the PSCAD data, in the PSSC data into PSCAD, and then model in PSCAD. Basically, let's say you have a in PSSC.dyr file and the raw file. The raw file .raw file is the power flow data file. .dyr file is the dynamic data file, which you have all the information of exciters, governors, stabilizers, and uh, many more dynamic devices, and all of them are already modeled in ETRAN library. So you can bring with a single click into PSCAD and do your PSCAD study in PSCAD. Let's skip this one. Network equivalent. This is one of the part that I want to discuss why we need network equivalence in EMT studies, because in power flow tools we have a full network model in power flow tools. Like, let's say, as an example, if you get uh, a certain country, entire network is modeled in PSSC or PSLA, Fortis Island, or any tool. The entire system is modeled. That is what we are talking, is thousands of buses is modeled in that particular tool. But when it comes to EMT, we're not gonna model all, let's say, hundreds of thousands of buses in PSCAD, because the phenomena that we are looking, or the area that we are looking, is much more smaller compared to RMS based tool. So we need to create a area, or the kept system, that we are more focused on in PSCAD, and the rest of the system we're going to model in a using network equivalence. So how we're going to do is using Electranix. We have, let's say, we pick 50 buses or like 20 buses as the area that we are doing our study, doing our renewable integration. There are a couple of buses, or there are few buses we can say as boundary buses, and those boundary buses we need to represent the rest of the system as multi-port network equivalent. So that way we can start the PSCAD study, or that we can start the EMT study with the correct power flow, correct initial condition, and then we can carry on with the contingencies or the disturbances that we apply in the PSCAD. So that's the main part. We need to have the correct initial conditions. That's why we need network equivalence. Parallelization. This is very important these days, because now large system PSCAD studies, or a large PSCAD studies, is very important when we have special phenomena that we didn't used to see before we have these renewable many more renewable integrations. So the when we have a lot of IBRs, or the renewable plants in a certain area, let's say it's very close by, then we cannot eliminate, or we cannot select such area without modeling those, or without having network equivalence. So basically we need to include those things, or we need to model all these devices in PSCAD. So when we do that, as I explained before, these are very small time step based studies. Very detailed level is model. So the processing power is huge. So when we have 50 models in one PSCAD case, it takes very long time to run if you don't put it in a correct format, or a correct PSCAD parallelization method. Because what we do is, using the inherent characteristic of a transmission line in the traveling wave model. In transmission line, it has a traveling wave delay. So if something happens in one end of the transmission line, it takes some time to see that thing in the other end of the transmission line. So that characteristic is being used to split a network into many cases, and that way we can process one IBR in a one CPU in the computer, and the next IBR in another core, or another CPU in your PC. So such a way that we can represent many IBRs split into several PSCAD cases and run them in parallel. That way we can optimize our computer processing power, and then get faster simulations. And co-simulation is one of the another technique that we use for the areas that we need to see uh, much more larger area that we need to analyze due to the type of the study. But we cannot do that huge simulation due to other processing limitations, or the limitation of lack of models, or things like that. And then what we do is hybrid simulation. What is hybrid simulations are, we model certain part of the network in PSCAD, the part that we need to see in detail, and the rest of the network, instead of static network equivalent, we keep that network in the RMS based tool and run them together. So the PSCAD and PSSC run them together, and then that way we do have the dynamic response of the RMS based tool together with the PSCAD, such a way that we lose some information, but we don't lose everything. So if you have network equivalent or the static equivalent, we lose uh, whatever the dynamic beyond that point. But when we have hybrid simulations, we lose certain things, but we don't lose everything. So that way, it's a compromise. So we have to, that's a engineering judgment that we need to take, where to where to keep our boundary buses, which part we're going to model in PSCAD and which part we're going to model in PSSE. These ones, especially the conditions like let's say after the contingency or after some disturbance happen in the PSCAD network, the machine angles or the entire network changes, and then we have a different power flow. So but when if we have static network equivalence, or the network equivalent in the sense the part that we not model in detail, those points the voltage will the angle will not be swing together, or the voltage will not be, voltage and the angle not change as expected in the actual system, because those are modeled as a static or the fixed voltages. So such a way that in that kind of situation we will have slightly different power flow than actual system. So that's why the hybrid comes into the picture. When we have hybrid, the boundary bus dynamics also captured, so that way we will have a better picture or a better system stability, sorry, not system stability, a better system representation in the boundary buses with hybrid networks. Also, any inter-area machine dynamics also we can see if we have hybrid simulations rather than static network equivalents. And another important part of a hybrid simulation or a co-simulation is the model incompatibilities, because sometimes we have the network in certain software and the device or the IBR that we are analyzing, or the wind farm that we are analyzing, PV, model in a different software. So we have to do the study and see how things go. So what we do is we can model that particular part, the wind farm or the PV in a certain software, and the rest of the network with a different software, and then connect together and then co-simulate the simulation and see how the behavior of the IBR. So that's one of the main use if we don't have the all the models in one software or the all in one tool. So to get a good idea where to put the network equivalent, or where do we need to use hybrid simulations to have a best accurate simulation results, that's the engineering judgment that comes from the experience, and then many more details that we need to see, and the type of the studies that we do, and many more things. So it's not very uh, straightforward answer where to stop or where to draw the boundary. So it's a very lot of details involved to take that decision, and that's a still people can do many mistakes, and maybe you model too much detail that you don't need, and you waste your processing power, or you uh, under model, or basically don't model the details that you need to see. So that's we have to carefully pick our study area and the simulation type uh, based on the study that you do. And alternative to co-simulation is basically we can use entire thing in EMT, or that is basically the compromise is your processing power. You do basically a lot of things that you don't require probably modeling in EMT, and then the simulations will be slow, and then still you can get away without doing co-simulation if we model everything in EMT. um, and there are many other aspects, limitations. If let's say if you don't have any models in certain tools, then there's no option to do hybrid simulations or core simulation, you have to stick into one tool. And this is one of the demonstration of the core simulation. PSCAD is one side and the PSSC is other side, and then we have a network disturbance applied in the PSSC side. So we bring all the network quantities, the channels that we need to see in PSSC side to PSCAD side and analyze the phenomena. So this is common. Core simulation is common when we have low frequency phenomena like SSR or wide area protection schemes that we need to model, full country kind of situation, that we keep certain area in PSCAD and the rest of the country in a PSSC or a PS Digital and Power Factory or different software tools. Summary: this is a little bit of a lot of data I given in within 50 to 45 minutes. EMT is great, but also complex. So there's many things, many details need to be analyzed, many methodologies, the way that you represent your network, where to draw boundaries, where to model, what type of studies that you do, and you need to get the models, regulatory frameworks, and basically you need to analyze the model, quality control, and many more things involved. So it is required, and it's not going anywhere, because it's more and more EMT studies are coming, because with the renewable integration and new problems comes when the system gets weaker. So uh, it's very useful. It'll be basically a must tool in many utilities, in must study in many utilities in future, because you need to see all these uh, behaviors. Basically, you need, before you connect an IBR, you need to see what happens if I connect this PV into this location. My entire network will go blackout, or do I need to do any augmentations and things like that? So you need to study these things. So this is very handy tool. So you need to basically involve many things, but at the same time it's complex. So very detailed modeling is involved. The only easy part is buying the software. So that's the easiest out of all these steps, but rest required effort and experience and study methodology knowledge and many more things. That's it. Thank you very much.
Thank you very much, Kasun. Like, I appreciate it for so many reasons, this presentation. The first one is for you to have the time to put everything together and so much knowledge. It's really incredible. And also a little bit of my of my background, like working a little bit with power transmission lines protection. Like the first example that I ever had when I got introduced to that was the first example you brought up on why do we need MTP studies. You know,
Mhm.
a simple first order circuit, you already know why you need it. So thank you very much. I have a question
Okay.
for you when it
Okay.
comes to feel that it's an example that's coming up, like especially like recently with a lot of like solar power plants.
Hmm.
Um, when it comes to the PSCAD code simulations, do you feel that for like studies as subsynchronous control interactions, is
Hmm.
it like a code simulation case or PSCAD has an alternative for that?
It is not a co-simulation case, because subsynchronous control interaction is a phenomena that you have two devices. Let's say, as an example, you have a PV in a certain location, and you
Right.
have a nearby another uh, another device which has a advanced controller,
Mm-hmm.
which those two controllers interact each other. Let's say you have
Mm-hmm.
a PV here, you have a STATCOM in a couple of buses away. You have a
Mm-hmm.
PV here, you have another PV or another battery energy storage system
Right.
nearby, or not specifically nearby. Let's say from certain electrical distance. Still, those controllers can interact each other and can
Mm-hmm.
create scenarios or the phenomena that the network can go unstable, or things can go bad. So if we need to see this control interaction, we need to have the both controllers model in detailed. So co-simulation comes into the picture, one of them in a RMS tool and another one in the EMT tool. So if
Oh,
you
I
do
see.
have in the RMS tool, you lose that one device's control detail is simplified. So you may not see the things that you should have been seen. So
Gotcha.
in that case, both has to be in the EMT.
Ah, perfect. No, that makes a lot of sense for sure. And one quick question, because we're almost at the top of the hour. It's about, you mentioned a lot on transmission line, the
Mhm.
models that you have on PSCAD. Something that I came across a long time ago is that I didn't have the option of, in another software, to simulate the transposition, like the geometric
Mhm.
transposition of lines. Is that something you can do with PSCAD?
Yes. It's very simple. So you can basically need to know the transposition location. Let's say you have
Right.
100 kilometer line, you have 30 kilometer transposition location and
Right.
another 60 kilometer transposition location. You simply model 3 transmission line, and then
Right.
you swap the faces, because these are not
Perfect.
single phase or a RMS based quantity. These are three
Mhm.
phase instantaneous. So you have three phase node and you have another three phase node right there. So you swap the
Uh-huh.
faces, uh, and then you
Oh,
connect each other. It's
no.
very simple.
No, perfect. Because the last time I had to do this, I had to use all the rotation matrix, you
Okay.
know. So that's like really
Yes.
useful. Oh, appreciate it so much, Kazum, again,
Okay.
and
Thank you very much.
everyone. Thank you, everyone, for being present over here with us. I just like to say for you guys that we're gonna have like a 15 minutes break right now, and then we're gonna have our fourth track with Eugenio Jaramillo and on writing a winning elevator speech and networking session. It's gonna be via Zoom. So if you
Mm.
guys aren't on the WhatsApp group or if you need the link, please feel free to reach out and please stay tuned. Thank you.
Thank you very much.
Thank you, Kazum. You guys have all a great day.